All right. Good afternoon, everyone. Welcome to today's seminar by Professor Paola Carbone. Professor Carbone got a PhD in material sciences in 2004, and after postdoc at the University of Bologna in 2006, was awarded a Humboldt Fellowship hosted at the University of Darmstadt in Germany. In 2008, she was awarded a Ruck Fellowship and joined the Department of Chemical Engineering at the University of Manchester, where she was promoted to professor in physical chemistry in 2020. Her area of expertise is simulations of soft matter, and her group specializes in developing new multiscale coupling procedures to link different modeling techniques from quantum mechanics to dissipative particle dynamics. Currently, active research areas include electrolyte graphene interfaces, polymer composites for industrial applications, and surfactant solutions. Professor Carbone, thank you for joining us today. We look forward to your presentation.
Thank you very much, and thank you very much for the invitation. I see there are 2 people in the waiting rooms. I don't know if...
I'll admit them.
All right, that's fantastic. Thank you very much again for the invitation. It's a big pleasure for me to be here. So what I'm gonna talk in the next 45 minutes, and please stop me if I actually exceed the time, is some of the techniques we have developed in the group to model polymers at interfaces. Okay. All right, so in particular, we'll focus on 2 different types of interfaces. So when the polymer is at an interface with the solid, so this is the kind of solid liquid interface where the liquid is the polymer itself. And then when the polymers are at liquid-liquid interface, so 2 immiscible fluids. So let's start with the first one, the polymer on graphite. So this project is in collaboration with Continental. So the interface between a polymer and a solid is a very common interface present in many polymeric materials. Of course, the one that comes up to mind first is polymer composites, where the matrix is a polymer melt, and inside the polymer melt you have fillers dispersed into it. So the project, as I was saying, is in collaboration with Continental, and so they were interested in a specific type of polymer. Continental is Carbone, so is a tire manufacturing company that makes tires. So the polymer they were interested in is polyisoprene, which is natural rubber, which is the polymer matrix for all type of tire. And the filler they disperse into it for the cheapest version of the tire is carbon black. So the interest for them was to predict the adhesion of a polymer on the surface of this carbon black. And as I'm going to show you, that means basically the adhesion of a polymer on a homogeneous surface. And the reason why they need a modeling technique to do that rather than is because the experimental characterization of the interface is very hard on their own. So what they were interested in is what is the feature of the surface of the carbon black to make sure that the filler disperses very well in the matrix. Right, so despite the image I had at the beginning, where I have the polymer matrix and then a perfect flat surface representing graphite. In the reality, the carbon black fillers that people disperse into the polymer into this polyisoprene matrix is not flat at all. So this is a 3D model of the filler itself. So as you can see, it's a very rough surface actually, rather than a perfect homogeneous one. And in particular, for carbon black filler, you can identify on this surface 4 different phases. The most abundant one is the graphitic phase. So this is represented by this dark black square, and basically crystalline phase of carbon. So it's a graphitic planes. Then you have amorphous phases, that is this light gray, that are usually between graphitic planes. and they come due to, so you have this because of, usually this carbon black is quite a cheap product, so it's obtained from pyrolyzed material, so you have a quite large amount of amorphous phase in some samples. And then you have two other phases that are called phase 3 and phase 4, we call them. And these are phases that are created by the overlapping of two crystalline phases. So two crystalline phases, so two graphitic planes can overlap like this, and they create these crystalline edges, or they can be nearby but forming a kind of well like this one. And so these other part of the surface, they are called slit-shaped cavities. So of course, my group develops molecular model, and therefore it's impossible to model the entire filler particle on its own as it is. We have to come up with a simplified representation of it. And what we wanted to make sure is that the simplified representation we use in our molecular model represents statistically the inhomogeneity of the surface of the real sample. So to do that, we develop a 2D model of the surface, and that's the way we do it. So let's assume that this is a simplified version of the surface, the homogeneous surface of the sample I showed you before. So you have some crystalline phases, some amorphous phases, and then you have these edges and slit. Apologies. Then what we came up with, basically, you can take this 3D representation of the surface and basically project all these four phases into a 2D flat surface. How can you do that? Basically, what we know from, as I'm going to show you some experimental data, is that the adhesion, so the adsorption free energy of the polymer on the four different phases is different depending on the nature of the phase. So, for example, in the amorphous phase, the adsorption is weaker than in the crystalline one, while the adsorption in the slit or the cavities like this one is higher than compared to the flat graphitic version. So what we can do is basically can represent this 3D inhomogeneity as energy points. So we can build a 2D flat surface and associate to each point of the surface an energy, and that energy will represent different phase of the surface. So for example, in this simplified case, the green bit represents the graphite, the blue one represents the amorphous phase, the yellow, these edges, and the red, the cavities. So in order to decide how many of these energy points represented by the phases we have in a real sample, we can use adsorption isotherm data. So basically, what Continental, have done in their labs is that they took some sample of their carbon black. Then they call it in different ways. So this is a sample called N115, for example, somewhat related to the number of the various phases you have in the sample. And then you characterize using measuring adsorption isotherms, taking the carbon black and using as a gas for the adsorption isotherm ethane, that it can be assumed to be a proxy of the monomer of polyisoprene. And then what you can come up is a distribution of surface defects based on the adsorption data that I'm not showing here. And then if you they convolute the peak of this distribution, you can come up with the relative percentages of the various phases. So for example, the one with the lowest energy, adsorption energy, is, as I told you, the one associated with the amorphous carbon, and the one with the highest, so as you go, you increase, basically you move to the amorphous, so the crystalline phases, the cavities, and the slit. So basically, what you can do is that if you perform this adsorption isotherm and adsorption experiments, for all the various carbon black, you can come up with an histogram like this. And the experiment tells you how much is the fraction of the various phases for that specific sample. Right, so then we focus basically then on 3 different samples, which are called in this way. So graphitized N220, this N115, and this channel gas black sample. And experimentally, so the experiments have been run on all the 3, and this is the percentages of the various phases you have. So for example, this one basically is all graphitic. Majority is graphite, and basically no presence of, there are no other phases. But the N115, for example, you see you have again higher percentage of graphitic phase, but you have a quite high percentage of also the amorphous and this slit. The channel gas black instead has still the graphitic phase is always the highest in percentage, but you also have very high value for the slit ones. So then associated to the various phases that I was telling you before, there are this adsorption energy, which are measured experimentally. And what we do is that we take the phase which has the lowest adsorption energy, we give a weight, so a relative weight to 1, and then we scale within our model the other phases based on the experimental data. So for example, the adsorption energy for the crystalline phase of graphite is assumed to be 1, and then inside the energy associated to phase 2 is 25% more, and so forth, based on these numbers. Then using this distribution and also using some specific rules. So for example, the amorphous phase is only between 2 crystalline phases. The phase 3 and 4, which are these plates, graphitic planes, either be on top of each other or forming a cavity, can be only between 2 graphitic region, but it cannot instead entrap any amorphous phase between them. So there are some rules to build the surface. And we have a Python code that basically is able to reproduce a 2D surface that statistically represents in terms of percentages and also relative position of the phases a specific experimental sample. So for example, this is pure graphite. This is N115, and this is instead, you see you have a lot of phase 3 here. This is this channel gas black. So we use this surface for our molecular simulation. Sorry. Oh, okay. So apologies. So so these are the experimental data. Using this Python code that we have, we can't, because we are constrained to the size of the surface, and the fact also, for example, that the graphitic patches we assume to be always for simplicity, really, square. So we can reach close numbers close to the experimental data. These are the simulated one. So the relative percentages are always okay, but you can see they are not exactly the same. Although, of course, this experimental number also have some uncertainty that usually is not reported in the experiment. Okay, so then we start to build. Now that we have a surface that statistically represents our experimental sample, we can start to build our molecular model. So this is the first layer of the graphitic surface, right? So what we do is that rather than using an atomistic model, we use a bead and spring, so a coarse grain model at quite a large length scale. And so the first thing we did was we coarse grained the surface. So these little dots here represent the atoms, and the larger spheres instead represents the beads that we map on top of the atomistic structure of the surface. So our surface at the end will actually be this form only by these larger spheres. And we assume a certain value. Okay, so this is a bit of a detail, but basically it's quite important to make sure that the size of the bead is commensurable with the distance between the bead. Otherwise, the surface becomes too energetic. But okay, I'm just skip this detail. Then we had to also coarse grain the polymer. So this, again, the smaller spheres represent the atomistic structure of polyisoprene. So these are the various atoms, this is carbon and this is the hydrogen. And so we coarse grain the polyisoprene chain using a kind of version of a bead and spring model. So this is the pure repulsive potential. So the WCA, so the pure repulsive Lagrange potential, represent the interaction between the beads along the chain and also with the other chains. The beads are connected to each other to form a linear chain through a Feeney potential, and we also have a bending potential between the three beads. And so these are the specific details of the model, but basically the point is that we have a coarse grain polymer melt on top of a surface. So the polymer, despite being a simplified coarse grain model, there are some details that, again, I'm not going to go into the details too much, but this represent all the details of the polymer model is in this archivics and also published now in Macromolecules. So basically the WCA model for the polymer can reproduce the mechanical properties and entanglement, number of entanglements corresponding exactly to polyisoprene. So at this length scale, the polymer is really polyisoprene. And then the surface is at the length scale of the model, again, an actual sample. Okay. So the first thing we did, so then the model at the end, the polymer system, so the simulation box actually looks like this. So we have the polymer on top, and then the surface, which is represented by, I think, 6 layers of graphene. So this layer that I showed you before with the various energy points. So the first thing that you usually do when you create a system like this is that you have to develop the parameters between the polymer and the surface. We did it with a specific procedure that is in the paper, but basically what we do is that we reproduce the mixing, basically the log piece, the solubility parameter of the monomer forming the polymer and the benzene. And we use Lennard-Jones potential to describe the interaction between the polymer and the surface. The surface is fixed in the space, so it can't move. And again, the polymer bead with each other interact to a WCA potential. So the first thing we did was, of course, to check that the coarse grain model represents our atomistic model, so the experimental sample. And the way we do here is, for example, calculating the density profile across the simulation box, measured perpendicularly to the surface. So the black line corresponds to the atomistic, black dashed line is the atomistic results, and these are two coarse grain model. In this case, the system is purely graphitic planes, okay, so it's the crystal structure. And we tried two different organization of the bead on the surface, so square lattice or hexagonal. So hexagonal is really mapping the coarse grain surface on top of the atomistic one, just to make sure that there is no effect at this length scale on the basically organization of the beads on the surface, and that has to be the case. You see that basically the results are exactly the same, and also the comparison with the atomistic model is reasonable. So we were happy with these results, meaning that our coarse grain model represents really polyisoprene on graphite. Okay, just go back. Okay, so we have a procedure to actually calculate the work of adhesion, so the actual free energy of adsorption of the polymer on the surface. But very quickly, here I just wanted to show you something else, which is that the wettability, so the ability of the polymer to attach to the surface of the filler, can, of course, correctly is measured through the free energy of adsorption. But you can also identify a proxy measurements for it, because calculating the free energy of adsorption takes a lot of computational power. And the proxy measurements that we use is this density fluctuation. So basically, if you calculate the inverse of the normalized polymer density fluctuation, so how much the polymer, so how much the density of the polymer in the proximity of the surface fluctuates over time, you can get information about how much the polymer is actually attached to the surface, and therefore a bit in a in a qualitative way, the wettability of the surface. And so these are the results basically. So if you have a filler that is purely graphitic, this is the results. So this is the heat map of the polymer density fluctuation, the inverse of the polymer density fluctuation. So as you expect, it's very homogeneous because the surface is homogeneous on its own. But as soon as you started to include some defects on the surface, this distribution, so these heat maps started to color different colors. So the height of the peak in the polymer density fluctuation, which in this case represents the darker color. So the height of the peak represents because this is the inverse of the density. So the lower is the density fluctuation, the better the surface is wetted. So from these results, what it clearly shows is that the fillers with the surface defect should be easier to disperse because they have higher wettability with the polymer matrix compared to the graphitic one. Then we also calculate other properties, but here I'm going to just show you the autocorrelation function of the end-to-end vectors of the polymer. So the reason why we calculate that is because this value is related to the glass transition temperature. So the change in local dynamics of the polymer chain is, as I was saying, related to the glass transition temperature. As the slower is the autocorrelation decay, the higher is the should be the glass transition temperature of the polymer. So the point was first to figure it out if we can identify what is the best sample to have the best dispersion to the matrix, meaning the higher wettability. And the second was what's the effect on the glass transition temperature for that specific filler being dispersed into the polymer matrix. So as you can see, so this light blue corresponds to the autocorrelation function of the polymer in the bulk, and then these are the autocorrelation function for the polymer when it's in contact with the various surfaces that I showed you before. So this is the pure graphitic one basically. This is something in between, and this is the one that has graphitic and basically doesn't have any amorphous phases. Apologies. So what you can see is that indeed the relaxation time changes of the polymer, indicating that the glass transition, at least of the interface, is likely to change. But what is also interesting is that if you look at this 2 value, it might look small, but the autocorrelation, if you integrate and you can really decorrelate completely, the integral, so the relaxation time of these 2 curves change a bit. And this indicates that basically, if you have, a polymer chains in contact with fillers representing the same percentage of phases, but different graphitic patches, they show a different behavior. So what it means is that what seems to be important is not only how much graphitic, amorphous, or the other 2 phases I have, but also the sides themselves of the phases. Okay, so then I now move on the second part of the talk, which is about liquid-liquid interfaces instead. Just to give a bit of overview, I think I missed a slide, unfortunately, for some reason. I don't know where the slide is. But basically, okay, so the solid-liquid interface is a very important interface, mainly for bulk polymer, so for materials for construction, for example, materials for construction. But polymers also find themselves at liquid-liquid interfaces. And 2 typical examples are when polymers are used for drug delivery, because the one way to deliver a drug is to encapsulate a drug into liposomes, for example, to make it more hydrophilic. Usually drugs are hydrophobic, so it's difficult to allow them circulation into the blood, in the bloodstream. However, these liposomes that are already used in the pharmaceutical industry have the problems that they have a very low mechanical properties. So they break up quite easily when they are injected into the bloodstream before reaching the okay, before reaching the organ where the drug has to be delivered. Therefore, in order to improve the mechanical properties of the liposomes, polymers are often included into the formulation. So the polymers found themselves at the interaction with the lipids, and so in a soft environment. The second situation in which polymer found themselves a liquid-liquid interface is during the process themselves. So, for example, one of the typical process, a chemical process to produce polymer nanoparticles is through solvent displacement procedure. This solvent displacement method is basically you have a vessel where the polymer is dissolved into the good solvent, and then you start to add bad solvent that doesn't mix with the good solvent. So the polymer should translocate from when the amount of poor solvent is high enough, will move from one phase to the other, and then will precipitate. This is a typical way of producing polymer nanoparticles. So studying the thermodynamics and dynamics of polymer liquid interface, it's an industrial problem and an interesting problem in industry as well. So we started to look at this problem from initially thermodynamic point of view, and we were interested in to determine the factors that to identify the factors that determine the stability of polymers at liquid-liquid interface. So do polymers prefer to stay at the liquid-liquid interface? They prefer to dissolve in one solvent or another? And then we were also interested in the dynamics of the polymer at these interfaces, and if the polymer microstructure affect the interface or not. So in order to do that, we initially again employed a coarse-grained model. So this in this specific case, we really lost any chemical specificity, and we just have a polymer that is described as a Lennard-Jones chain and two immiscible fluids, which are also described through Lennard-Jones fluid. So what we did, we calculated the potential of mean force. So basically, in this case, we really calculate the free energy of the adsorption in this specific case from the interface to the bulk liquid. So we have the polymer at the interface, we pull it away from the interface into the bulk liquid. And this liquid is immiscible, so the two liquids are immiscible, but they are the same type for the polymer. So in one case, the liquid is a poor solvent, so the polymer doesn't want to dissolve in it. And in another case, this is the case, and in another case, instead, the two liquids are immiscible, but they are good solvent for the polymer themselves. So what we found is that irrespective to the quality of the solvent, the polymer tends to reside in the interface all the time. This indicates it's very hard to actually dissolve a polymer into a solvent. For example, if you use a solvent displacement method, because the polymer wants to stay at the interface. This is the potential mean force of moving the polymer from the interface to the bulk. And you see it's positive, meaning that you actually have to add work. You have to do work to pull it away from the interface, even if the solvent is a good solvent. So if you plot the free energy of desorption against the number of monomers along the polymer chain, what you find, okay, here there are a lot of numbers, but basically you can, a lot of points, but basically what you want to see is just that this number goes up. So the longer is the polymer, the more the polymer wants to stay at the interface. So this indicates that even chemically homogeneous polymers, such as those that are not amphiphilic, they are surface active. And so there is a certain dependence on the morphology. So we try linear polymers, star polymers as well. And we also look at good solvent and poor solvent, as I mentioned, and this free energy is always positive. That it becomes more positive for good solvents. So if the two solvents are good solvent, it seems to be even harder to detach the polymer from the interface. So why is that? So the main reason is why this free energy is positive is due to enthalpic reason. So the polymer basically what it does is reside at the interface, and doing that reduce the overall free energy of the system, because it screens the unfavorable the unfavorable interaction between the two solvents. And that's why in this free energy of desorption increase with the molecular weight, because the larger it is, the polymer, the higher is this interfacial area. So the area occupied by the polymer at the interface. if you measure the polymer entropy, so of course in the free energy there is also an entropy on the solvent, but this can be assumed to be not important because we have a very simplified solvent in our case. But what we could change instead is the polymer entropy. So this is basically, which is of course conformational entropy. So we can calculate the conformational entropy just looking at some distribution of some parameters, such as we did the end-to-end distance and also the dihedral angles. And so this is the difference in entropy when the polymer is at the interface and when the polymer is in the bulk. So usually this conformational entropy is a very important value to determine if a polymer is adsorbed or not on solid interfaces. But what you can see from here is that really the entropy change in entropy of the polymer is almost negligible in this case, because the interface is soft in this case. So the conformational entropy loss when the polymer is adsorbed and the interface is minor. Then we moved on in looking at the dynamics of the polymer. And what we found is, again, something I think interesting. So let's say, again, these are the two immiscible liquids. We have the polymer at the interface, and then we calculated the dynamics. So we calculated the dynamics of the polymer at the interface, for example, looking at the dispersed displacement in this case over time. Then what we found is that when the polymer is confined in a 2D slit, let's say, which is soft, then its dynamics still follow the Zim model. So it's like if it's in pure bulk, sorry, if it's not confined in the slit really, it's like if it's surrounded just by solvent. However, when you physically confine the interface, and so you add, for example, two hard walls so that the polymer can't move, then the dynamics switch to Rouse dynamics, and this, which is the same dynamics that polymer have when they are adsorbed on the solid surface. Then we were interested, so the model is still very simplified, but we can start to add a bit of complexity. And one thing we did was to change the viscosity of the two fluids. So these are still Lennard-Jones fluids, so simplified fluid, immiscible still, but one fluid has a higher viscosity than the other one. To change the viscosity, we use two procedures. I just want to mention this one here. So basically, there is a correlation equation, which is something like that, that relates the viscosity of a Lennard-Jones fluid with the sigma of the Lennard-Jones particle. So in doing that, you can change the viscosity of the fluid, not much, but you can still, but we wanted to have, so if you want to go above and have a very viscous system without crossing the boundary of the phase of the Lennard-Jones phase diagram to the solid, then you can't use just the Lennard-Jones fluid. You have to start to use dimer or trimer, etc. Then you can increase the viscosity even further. So in this case, what we found is that the polymer, even when the viscosity of the two fluids are different, the polymer is still trapped at the interface. But we found that when the difference in viscosity between the two fluids is fairly small, like in this case, then the dynamics of the polymer still is follow a Zim model. So it's like if it's dissolved in the fluid. But when one of the two fluid it's much more viscous than the other one, like the red points, then the dynamics switch to a Rouse dynamics, which is the one typical of a polymer melt. And we did this calculating many properties, and this is just again the this is the relaxation time of the end-to-end vector. And we justify this looking at the number of fluid beads that are around the polymer over time. So basically what happens is that it's quite obvious to some extent. So when the fluid is very viscous, then we have a lower number of liquid molecule, lower number of solvent particle near the polymer, and therefore the screening effect of the hydrodynamics that usually happens in a Rouse dynamics is present basically. So the hydrodynamics effect are screened basically when the fluid is very viscous. So then it looks a bit counterintuitive, perhaps, that when you have a polymer at the interface between two liquids, and one of the two liquids is a good solvent for the polymer still prefers to stay at the interface. So we actually did this simulation on an atomistic model, and this was a polyethylene oxide chain. We had a water and a hexane, so two immiscible fluid. Water, of course, is a good solvent for this molecular weight for the polyethylene oxide, and hexane is not. And we did, again, the free energy calculation. So we have the polymer, in this case, the polymer was in water, and then we drag it across the interface up to the hexane phases. And what we found is in the free energy profile is this well, indicating again that the polymer would stay at the interface even in this situation. So confirming this experiment, so these results we found with the simplified version of the polymer. And if I have time, maybe I can very quickly just mentioning some other work we have done with the block copolymers. So far I discussed about homopolymers, but of course, majority of the polymers used in the pharmaceutical industry, for example, are actually block copolymers that are basically amphiphilic. And pluronics, which is a block copolymer of polyethylene oxide and polypropylene oxide, are typical polymers used in the pharmaceutical industry. So we have a model, atomistic model for polyethylene oxide. And what we were interested in is in developing this hybrid liposome that I was mentioning before. So incorporating polymer into a lipid bilayer, basically, so a lipid liposome. And the reason for that is because a liposome in which polymers chains are embedded in should have better mechanical properties than pure liposomes, and therefore should be better as a drug delivery system, which indeed they are used for that. So in order to do that, basically what we did is we couldn't model the entire liposomes, of course. So we had a lipid bilayer with a specific lipid that in this case was a DPPC, very much used in the pharmaceutical industry. This is water, and this is our block copolymer. So what we did in the simulation is that we let the polymer to move. It was dissolved into water initially, and then what we saw, exactly as we saw in the previous simulations, the polymer attached to the surface. But in this case, it was actually slowly being dragged into the lipid bilayer. So once the polymer was inside the lipid bilayer, then we could apply a tension and look at how the mechanical properties of the bilayer was changing once the polymer was embedded into it. That's exactly what we did. We basically we had a lipid bilayer with the polymer in and the lipid bilayer without the polymer, and then we just pull it. We pull the system and we calculate the lateral pressure as a function of the area of strain, so how much actually we were straining it. And these are the results. So these are the results for the pure DPPC. This empty, so we had an empty symbol when the membrane broke, basically. And these are the results when the DPPC incorporated a specific pluronics in different percentages. So this color is the one with the highest value of polymer, and this is with the lower value of polymer. So what you can see is that basically before rupture, the lipid, so the system, the hybrid system, let's call it, where we had also the polymer incorporated, are able to sustain a higher lateral pressure than the pure lipid. And also the compressibility modulus, so this time we compress it, also the polymer, the system with the polymer incorporated, but in a low ratio, show a better mechanical property. However, there was a problem. So the mechanical properties were okay, but if you run the simulation for very long, what happens is that you actually see a formation of a pore. So basically the lipid bilayer form a pore and then detach. this everything was very much dependent on the amount of polymer you have and also the number of monomers, of hydrophilic, hydrophobic monomers you have within the polymer. But the pores was forming. And not only a pore can be formed, but also what happened, we also investigated what happened when you change the temperature. So again, once the experimentalists make this hybrid liposomes, they call it, then they have to store it. So it is known that, of course, I mean, lipids as all this liquid crystal system, they have a phase diagram as a function of temperature, and they go through a subgel phase to a gel phase to a liquid crystal phase, depending on the temperature at which they are. So we were interested in, so first we tested the mechanical properties, and then here we test what happens, how the hybrid polymer lipid membrane behave changing the temperature. Okay, just show you the next slide. Okay, so what we calculate is an order parameter, which is basically a value that tells you how much is how the level of order in the tails of the lipids, so in the part of the lipid bilayer, in the internal part of the lipid bilayer, the hydrophobic part. So this bit of the lipid bilayer has a different level of ordering. He's doing everything on his own. Apologies, has a different level of ordering depending on the temperature. So the results you have for this order parameter for the pure lipid is something like that. Basically, a raw temperature, you have a high order, and then you have a sudden jump in the level of ordering at around 298 Kelvin. This is this transition I was telling you about from a gel phase to a liquid phase, and this is a first order transition because the transition is sudden, and you can see here as well looking at some other order parameter. But what you can see is that when the lipid incorporate the polymer, then you still have a reduction in ordering as you expect, so you still go to the liquid phase. However, you see that is much more smooth. There is not a drastic jump. That means that the incorporation of the polymer, what it does, it changes the nature of the phase transition from a first order transition to a higher transition. I would say a second order transition. I don't know why, so apologies for that. He just is his own life. So, and you can see this also on the structural properties. So depending on the temperature, as I was saying, a low temperature, you have a crystal phase, and then you go through a mixed phase, which is called the ripple phase, where you have a bit of order and disorder, and then you go to the disorder phase. So these are the results for the pure lipid, as you expect. You can measure this again with this order parameter, which is this bond order that tells you basically in this specific case the amount of hexagonal phases you have in the system. When you have the lipids, when you have the polymer inside, what you can see again, so the pure lipid again show this peak indicating a first order transition. When you have the polymer in, you don't see that. Is again very, very smooth. So with this I finish. I want to thank the sponsor for the various projects I show you, and these are all the people that have been working with me in the last 7 years now, and thank you for your attention.
Thank you very much for your time and for a lovely presentation. I was going to say, I'm sure we'll have questions today, but I can see there's already one. Paola, please go ahead.
Thank you very much, Professor. I would like to ask a question with regards to the star polymers. If you see, what's the biggest difference between the linear chains and the star polymers that you see?
Yes. So basically, everything is due to this the amount of areas. So basically, everything is dominated by how much the polymer is able to screen this repulsive interaction between the liquid. So a star polymer can, if depending on if you have a good solvent or a poor solvent, if it can screen better the interaction, so basically means if it has a higher interfacial area, then it will reduce the free energy even further, and therefore the free energy of detachment is going to be higher. So the morphology of the polymer starts to play a role when it can really, the polymer can really spread out. That's why the detachment free energy is lower for poor solvent. This is not because, so it's very counterintuitive, because you can imagine if you're trying to pull a polymer out away from the interface into a poor solvent, it shouldn't like to go there. However, this is less energy costly than detaching it to move it into a good solvent, because the fact that it's a good solvent, two liquid are good solvent, allow the polymer to spread at the interface, and therefore this interfacial area is higher. I don't know if it's clear what I'm saying. So it's very difficult to predict. Everything depends how much the polymer can really spread and screen the repulsive interaction between the fluid.
So this star polymer, what kind of star polymer is it?
Yes, I have it, unfortunately I don't have it here, but this is a real star polymer. So you have a bead in the middle and then a lot of branches coming out. And we were changing various stuff. So we kept the number of monomers constant. So let's say we had, I don't know, 20 monomers in the linear chain, and then we build a star polymer with 20 monomers. But for example, you know, like 5 branches with 2 beads each, or 2 branches with 5 each. So we kept the number of monomers constant, and we're changing the topology. But it's a proper star polymer. So you have a monomer in the middle, and then like branches coming out.
So the morphology of the star polymer will play a crucial role.
Yes.
I presume, if you change the number of atoms.
Yes, absolutely. So everything is down to how much it can expand at the interface and screen the repulsive interaction between the two fluids. Everything is down to that. Of course, this is a simplified model. So if you have, for example, hydrogen bonding, the numbers might change. But when we look at the polyethylene oxide that can form hydrogen bonding water, for example, we still saw that the polymer wants to stay at the interface to reduce the interfacial tension, basically, between the two fluids.
Yeah, because I would expect if it's a very spherical with many arms, this effect would be reduced, perhaps.
That's correct.
Compared to ones with which can take more linear and spread out better.
That's correct. Yes, that's correct.
Thank you. I really appreciate it.
Thank you.
It's very interesting.
Vangeli, please go ahead.
Yeah, so thank you very much, Paola. It was very nice, and you cover many different things. So,
sorry, I hope I'm not. Someone, is it me that froze?
No, I think Vangeli.
Okay.
Okay, let's maybe move to the next question. Anastasia.
Okay, thank you very much. Very interesting talk, Paola. In fact, I have 2 questions. The first is in the case of the liquid interface between polymers, where you said that the conformational entropy of the polymer chain is more or less the same for all cases.
Yes.
I'm wondering if this is dependent on the size of the polymer chain compared to the size of the interface.
Okay, that's a good question. So there is a simplification here, which is that we have only one polymer chain. So it is possible that the concentration of the polymer might change the result. So I know that some experiments done years ago, they were showing that the migration of the polymer was indeed driven by conformational entropy when the concentration of polymer was very high. But in our case, in this specific setup, I don't think we could appreciate that because the interface is much larger than the size of the polymer. So there is no effect in that sense.
This is exactly my point. Because the interface is much larger than the conformational energy is okay. And if I may, a second one to the part of the blocopolymer with DPPC. I'm not sure that I catch it. It was a coarse-grained model or an atomistic simulation?
Atomistic.
Atomistic. So in that case, did you also try to compare similar measures with a homopolymer instead of a blocopolymer?
No, we didn't, because you need amphiphilicity. So you need, because the polyethylene oxide is the hydrophilic one, they make sure that the length is the right one, etc. So it's hydrophilic, and you need an hydrophobic because otherwise, I think it will not penetrate inside. So is the PPO, which is the hydrophobic bit, that really grab, which is also the majority. So you usually have a higher number of PPO monomer into your polymer, and is the one that drags the whole polymer in. It's also used in flip-flop, actually, which I haven't showed. So you can't do this with the homopolymer.
Yeah, because I'm thinking the case of the fracture of the system will be different if you have a homopolymer. The limit that you that you found that there is a fail. Yes,
I understand what you say. So we tested different so we tested different blockopolymers with different percentages of polyethylene oxide and polypropylene oxide. So we were varying the hydrophilicity overall of the polymer chain. We did all this, both the simulation when we apply a tension and the simulation when we change the temperature on a specific block copolymers with a specific number of PO and PPO, which is the one that is used in industry, which is called L64. They have a very weird names. I am sure that the value of, for example, the fracture here is going to change. But what we were interested in, it was to see if it's indeed true that if you include the polymer, then the whole system becomes more elastic to some extent. So you can pull it more. And it looks to be the case, but it was quite interesting to see that if you put too much, then this improvement is reduced. But he's probably right. But you know, they all basically break a similar percentage. So I don't think you can really make a polymer, a lipid membrane, which is still a lipid membrane that can really stretch more than basically 70% before breaking.
Okay. Right. Okay, thanks a lot.
Thank you, Anastasia. Nice to see you.
Vangelia, I see you back.
So sorry, can you hear me now? There was apparently a problem with the network. Actually, today it's all the day it's on and off. So I was wondering, Paola, so at some point, maybe you discussed that already. So there is this chain that is going between the two different, let's say, solvents in order to reduce interfacial tension. I think it was a little bit below, right? It's not so clear to me the reason for that. So apparently this chain is not, let's say, it's not as bad the interaction with the poor solvent comparing the interaction between the good and the poor solvent. Am I right? So I mean, this should depend on the type of interactions between the two solvents as well.
Okay, well, definitely it will. So, sorry. So we made sure that the interface was quite sharp. So between the two liquids. So the interfacial tension, I guess we calculated that. I don't remember how much it was, but it was still everything reduced unit. So the numbers themselves don't make much sense. But basically, you see that the interface is sharp. So the interfacial tension was high enough. Of course, you know, if the interfacial tension is lower, then this effect of the screen is going to be reduced. But normally, when you try to dissolve the polymer in a solvent or in another, like in this industrial processing with the solvent displacement procedure, they have to be immiscible. the two solvents are immiscible. So one is, for example, water. Normally you have water and another solvent, and so they are immiscible. But you are right. I mean, the free energy of desorption will depend on how much the two liquids hate each other. Yeah.
I'm just trying to understand. So in this case, let's call it a purely enthalpic effect, because as you said, when you have water, then you have on top of that the hydrophobic effect, which is partially entropic due to the modification of the hydrogen bonds, let's say, network. So, but in this case, you don't have such an interaction. So it's purely enthalpic.
This case is pure enthalpic because we don't, yes. Yeah. But,
but in the atomistic one, there was the,
But yes, and so the change in entropy was also for the chain only, as you said. But when we move to the atomistic one, we still saw, you know, the well.
No, here because you have the water, so it's clearly also the hydrophobic effect.
Yeah.
You're right, yeah. Okay, and if I may, one more, in the first part now, at some point you present the density, for example, profile.
Yes.
So, okay, the agreement is not bad, as you say, but on the other hand, you know, we have seen quite often that such differences might be important for many properties, actually, the interface. For example, for the friction, the viscosity of the interface, or even the mechanical properties. So, did you try or did you consider how to modify, let's say, interactions in order to represent better the density profile there?
So I think the problem of the density profile is just the fact that we have very large beads. So this is a bead and spring. So each monomer, so each bead represents 70% of a monomer. And also, you know, it can pack much nicer because it doesn't have all the little atoms that the actual atomistic system has. And that's why we have much nicer peak in the coarse grain model.
But in the atomistic here, the analysis, again, I assume in a kind of monomer-based profile, right?
Yes,
or
they
it is
are.
the monomer?
No, it's the monomer. We did this mapping as well. Okay. But of course, in the atomistic model, it's really impossible to pack it as nicely as a WCA. So we knew that there was this problem. We haven't checked definitely we haven't checked the friction, and we also haven't checked the viscosity. But one thing we checked, which I haven't shown here, are other dynamic, not dynamic, other structural properties, number of loops, trains and stuff, and they match nicely. But it could be that viscosity, I mean, yes, it is possible that the viscosity is going to be different also because the model is, the coarse grain model is not to match the viscosity. However, the coarse grain model that was developed by Karsten, you might know, and is able to reproduce the mechanical properties, some of the mechanical properties, so the oscillation, of the bulk, yes, of the bulk,
Okay. Okay, thanks. Let's have more questions and then I might come back.
Vanis, please go ahead.
Okay, thank you for the very insightful presentation. I have a couple of questions, initially concerning the first part. Didn't quite follow the how the coarse-grained model describes the surface roughness.
Yes, okay, sorry, I know.
How it captures.
Yes. So basically the point is this. This is the physical surface roughness. We know that surface roughness is given by 4 different phases of the carbon, which are these 4. Then you can calculate, you can measure the percentage of the various phases experimentally for various samples. And this is done here. And you can still experimentally identify the percentages of the various phases. So what we did basically, we said, all right, so I have the various phases, graphite, amorphous, this one and this one. I can project these phases into a 2D flat square, basically, and assign to the points of this square, basically the overall one, different energies, which is just the Lennard-Jones parameter, the epsilon in the Lennard-Jones parameter that is used to interact with the polymer, that represents the experimental data. I don't know if it's clear, so how it's saying. So for example, phase 1 is the one that adsorbed the least, right? So, and phase 2 is the one in the middle, for example. Then I can say, okay, so if this bead specifically, this one, okay, maybe I can go to presentation now. This one, for example, this one, if this represents graphite, then it's going to interact with an epsilon equal 1, for example. If this one represents the amorphous, I know the amorphous is 25% more adsorbing, then the interaction will be 1.25. I don't know if it's clear. So this is the translation from a 3D roughness to a 2D, let's say, through the energy points. And then what we do is that we have this experimental data from various samples. And then, okay, let me do this. And then we have a Python code that is able to build this massive, this square with the correct number of gray points, red points, blue and yellow, depending on these percentages.
Okay.
And we can do that because there are some rules. So for example, the blue points can be only between these two, for example. The crystalline edges and the slit cannot be close to the amorphous. So there are some rules that we apply within the Python code, and we end up with the percentages of the phases that are similar to the experimental one. So the experimental one are these numbers, for example, and our simulated sample is this one.
Okay, but I suspect that with coarse graining, you might lose some roughness effects by regrouping, by grouping several atoms. But this is inevitable, of course.
Yes, but to some extent, these are also rough data in the sense that the adsorption is done for the monomer, well, a bit smaller than a monomer. So we thought, okay, because these are energy associated to the monomer, so to the ethylene, which is half the monomer really, then it's okay. But what we are definitely missing is the physical roughness. So the fact that if the polymer is entrapped, for example, here in the slit, it's not only more attracted, but it's also changing conformation because it gets, for example, thinner. And we lose this because this thing, this 3D thing, basically, is represented with a point. So we lose the change in the effect on the conformation of the polymer chain, which we know, well, people think it has an effect. There is a bit of debate on that because Continental thought that there is a name for this, pine effect, I think it's called. We lose that one because we don't actually have a 3D roughness, it's a 2D one.
Yes, yes, it's inevitable. Okay, and another question concerning the filler concentration. I saw you. I saw that you examined filler concentrations corresponding to experimental ones. I assume that there must be some critical filler concentration when where the fillers counteract in the wettability of the polymer chains by forming, for example, aggregates. But I guess it's not examined in your work.
No, it's not. Actually, this is the next point. We would like very much to do that, and we have in mind how to do it, but we don't have the students. So, so we have a PhD studentship. Maybe I can send so that's exactly where we want to go next. Yeah, thank you.
Manpower. Yeah. And one last one concerning your second part for the liquid-liquid interface. I suppose that your model in the case of good solvents, if you change the head and tails of your polymer chains, then you would have a surfactant effect, more or less. Would it be something like that, I guess?
That's true. So
these interactions could be tuned then, yeah, in order that the polymer acts as a surfactant between these two different phases. Okay.
That's true, but basically these results show that even if you have a monopolymer, so it's not a surfactant system, it's just only hydrophilic, it still stick to the interface as much as the surfactant would do. But yes, you're right.
Okay, thank you very much.
Yorgos, please go ahead.
Hello, thank you, Paola, for your presentation. I would like to ask something regarding the pluronic polymers. Do we know something about their in vivo toxicity? Because I see that they act like micelles. with the hydrophilic and hydrophobic part. Do we know if they are toxic in vivo?
They are toxic, yes. So we actually started to work on this long ago in 2012, and this is a project started with the people from pharmacy, and they were interested in it to predict the toxicity, and they are toxic. So in large quantities, they are toxic, and they release basically. So the spore formation that I show, probably it's very hard to say in a real cell, but it might be one of the mechanisms by which they actually create a pore in the membrane of the cell, and so the cell dies. So we had done, so it depends on the percentage, how much polymer you have, and also the relative ratio of the various monomers. Some are more toxic than others. But we move on from that to, because then the pharmaceutical people, the people from pharmacy, rather than be interested in seeing the toxicity of the pure polymer, they were more interested in see if you can amalgamate them with these liposomes and then create this carrier. So the tests on the toxicity were done on the pure polymer, and the pure polymer is toxic.
I understand, but if you manage to have a low concentration from this, I think this will lower the toxicity, probably. So
Yes.
it's a matter of, it's a rule of the toxicity, how much you have, and if you increase the concentration, maybe it becomes toxic. But I don't know if even at low concentrations this is toxic.
So to be honest, I don't remember, but what I remember was that in some cases, if they were not toxic, the pharmacists, they believed that it was because they were not interacting at all. It's like if they were not there. So they were dissolved in the solvent, which was salt water, and that's it. They were just not interacting with the cell at all. That was red blood cell they did the test with. So they thought it's not that they are non-toxic, it's that they just don't do anything. They're just not interacting.
Okay.
Their own.
Thank you.
I'll ask a question then. So do those polymers then affect the liposome's ability to recognize a target cell? Is that what's happening there?
No, they
Not.
don't. So that was I think you have to add other stuff into it. But the whole point was because basically when you put liposomes, you put a drug or whatever, even aspirin into this liposome, the liposomes break very easily. Just if you have to inject it to an injection, then it can even break just because you inject it, or they can break through the bloodstream. So in the pressure of the blood, they break before reaching whatever organ they have to target, and because they are just very easy to break. So the idea was to develop this hybrid, to adding a bit of polymer in, so that they would not break basically before reaching whatever organ they had to reach. But they would not, as they are, they would not just improve the targeting property, let's say, that you have to have something else.
Okay. Are there any other questions? Professor Carbone, I didn't ask you how much time you have for questions. If you have any.
That's fine. Please call me Paola.
Okay. Okay. Vangeli, you said you had more questions?
Yeah, we will not allow her to leave before take some time. I'm just kidding about it. So just actually you mentioned already about the interfaces, all this, as you said, the conformational, let's say, the changes at the interface that of course it's not easy to be captured. And you are right, I think one of the reasons for the pain effect is assumed to be these conformations at the interface that are changed or not changed under deformation. So I'm just wondering about that, because in that case you have also metastable, let's say, conditions. So is there any other way indirect, for example, by introducing additional bonds with the interface? Let's say not permanent bonds, but temporary bonds, in order to somehow enhance such differences at the conformational level?
To be honest with you, I don't know. So that was a discussion I had last face-to-face conference I went to. The problem, of course, is another one as well on top, I think, which is the fact that you are interested in this pain effect under process condition. So during mixing, for example, so out of equilibrium. And of course, that's not the case here. We are complete equilibrium, which absolutely doesn't represent at all what happens when they actually mix this stuff. Adding bonds, I don't know. So the idea is to develop a homogeneous, homogeneous model. So to homogenize basically the whole sample with a lot of filler in, using homogenization procedure that is used for this composites, and use some information from simulation, including resolving locally some of the mechanical properties and give it to the homogeneous model. Yeah, but that one will still be at equilibrium.
Yeah,
so
correct. But
the very big challenge is to go out of equilibrium.
Even for this case, even at equilibrium, you expect that the mechanical properties will be affected by the local, let's say, conformational changes. That will be different than you have far away from the surface. So the question is how you can, if it is possible, to describe that. I mean, this idea of bonds that I've told you, it's something that is coming from also our research as well. So we have a collaboration with Marcus Müller where we use this slip spring model in the mesoscopic level. And there the idea is to introduce actually fictitious bonds in this mesoscopic level in order somehow to describe the...
You need to have some kind of experimental data to fit against.
Yeah. In that case, we had the atomistic one, but you are right. You need to have some data. Okay. And another one now, as you said, for the experimental data, if I'm not wrong, you use data from ethene, right? Ethylene. From
what?
From acetylene, about the adsorption.
Ethylene.
Ethylene. Yeah, ethylene. It's ethylene, right? Ethylene. You use data about from the isotherm of adsorption.
So it's a C2H6. Yeah, I don't know why I wrote 2. You are right.
It's C2H6. Okay.
Yeah. You're right now, I think.
So it's ethane.
Yeah, ethane.
Ethane, okay. I was wondering actually how different this could be from the monomer of polyisoprene.
Okay. The monomer of polyisoprene is a bit...
Yeah, you have the side group, you have 5.
Yeah, of course, yes. I mean, yeah, they haven't tried with isoprene. I think the reason is because you need to have a gas phase. So
definitely. You need the gas phase for that.
So it's a very rough, that's what I was saying, even the experimental data are an assumption. So I think it makes sense to have a coarse grain model and definitely not use this data to develop an atomistic model because the data are too rough. And it is not an actual monomer, that one.
Definitely. No, the other way is to have, let's say, atomistic data and try to parameterize the coarse grain based on the atomistic, of course.
Yeah.
But that's another route, let's say. And for the dynamics below, probably the last one, just for the dynamics, I think you mentioned about the end-to-end vector autocorrelation function, right?
Yes.
Did you calculate the segmental? Because the TG is traditionally more related, let's say, with the segmental dynamics.
So we haven't calculated TG at all. It was just a kind of extrapolation to what might happen. So we calculated the G1, G2, the various mystical displacement of the second mass. Then we calculated another thing which I don't remember.
No, Paola, I was referring more to the first part. So somewhere you calculated the correlation function. I think it's a little bit above. Here, it's 15. Slide 15.
This one. All right. What did you say?
No, so if I'm not wrong, you discussed that also with respect, as you write there, the glass transition temperature. But I just mentioned that for the glass transition, typically we use the segmental dynamics.
No.
So, I mean, experimentally from the electric spectroscopy, typically the segmental relaxation time is used in order to determine the TG. So I'm just wondering whether you try to calculate a segmental based.
No, we haven't.
Relaxation time. Okay.
But that's a good point. No, we haven't. Okay, thank you. That's useful.
And here the relative difference now, it seems that it's considerable. Yeah? It's considerable. Actually.
Yeah, it is. But what also was interesting for us was this one. So what is the size of this patch? Basically, so when we build these surfaces, the first thing in the algorithm that we have to decide is the size of the graphitic patch. And then basically we build everything else around them. So how big it has to be? So the experimentalists, they believe that the size of the patch has to be roughly the size of the radius of gyration of the polymer. Then what we did is we built two different models with the same percentage, right? With the same percentage, but different size of the patch. And the result seems to be affected by that. So the experimentalists, so
No,
making this assumption might be wrong, because of course I don't know how big this patch is.
No, but this is interesting. It's interesting because that's what I would expect. It's not. I don't think that it's surprising. Yeah, and just to make it a little bit more harder for you. I mean, the results would depend also. I would expect that they will depend on the distribution of the different, let's say, kind of points, energetic points that you have in the system.
Yes.
Right. So did you try different distribution for these systems, let's say, with the same average number of points, but with a different distribution for them?
Right. Okay, that's an interesting question, because there are some papers actually published years ago but the point for us was that we wanted to represent the experimental sample. We didn't want to create a distribution that was not representative of the experimental sample. So we are bounded to some rules. Okay. You know, so for example, the graphitic points have to be all nearby. It's not, you can't have a graffiti point here, graffiti point over there. It has to form a patch. So the amorphous has to be between the patches. The other two cavities has to be in between the patches and stuff like this. So we had some rules, and we didn't want to create a random distribution of these points.
So just from curiosity, how well characterized are these samples experimentally? Do they have exactly the exact, let's say?
Well, as long as you believe they are numbers, you know. So these are the numbers. Doing this adsorption stuff.
This is the average, yeah, but do they have also information about the distribution, let's say, of this? Yeah, apparently they have some.
No. So, they just know on average, you have this amount, and this amount. Then they know, I think with the STM, the size of the graphitic patches. And then we know, because of the way we structure this stuff, that, for example, between 3 and 4, everything has to be graphitic here. You don't have any amorphous. You know.
And this is for carbon black, but not, is this for the nanoparticles? Because in carbon black, you have the nanoparticles as well.
Yeah, but experimenters don't use it. It's too expensive. So
so they use this large.
Very cheap, you know. So the idea was really to represent their experimental sample. And they don't use nanoparticles or anything like this. It has to be very, very cheap.
Okay. Thanks, Paola.
Thank you, Marianne.
I think if there are any other questions, people can unmute their microphones and ask. Okay. Well, Professor Paola, thank you very much for your time today and for presentation. It was really lovely, and I feel what?
No, there is a bit of echo.
Oh, that's strange. I'll keep it brief then. Thank you very much for a lovely presentation. Good afternoon, everyone.
Thank you very much for the invitation.
Thank you very much.
Thank you very much, Paola. So next time we hope to have you here.
I hope so.
Take care. Take care.
Thank you.
Thank you very much. Bye-bye.
Bye.